Welcome. Just to review, we have a traditional von Neumann SmartNIC with the network on the left, the SmartNIC in the middle in green, and host memory on the bottom. Network traffic comes into the transceiver on the left, travels through the network classifier logic and into NIC memory. When an ARM core is available to process the traffic, it pulls it back from NIC memory. Once processed, it will sometimes be written back to NIC memory, awaiting the PCIe logic to eventually write it out to host memory in the server. Best case, the ARM core decides to drop the packet, and this results in 2 memory accesses. In the case of an exception, 4 or more memory accesses could be required to process an inbound packet. This demonstrates that memory accesses are the bottleneck for von Neumann SmartNICs. So how do we address the bottleneck problem? We solve the underlying memory problem by scaling up the architecture or the type of memory used in the system. We'll look at both solutions. First, going from a single memory channel to multiple, then review the other memory options available from DDR4 to GDDR6, as well as memory within the package. So far, we've assumed that all memory uses a single channel of DDR4, which is 204 gigabits per second. If we jump that up to 2 channels, this would be about 408 gigabytes per second. Doubling the number of channels only delivers about 70% performance gain, but to keep things consistent, we'll stick with marketing math. If we were to double this again using a 4-channel memory architecture, this would provide 816 gigabits per second of memory access. In a previous video, we showed that 840 gigabits per second of memory access was required to satisfy 50% NIC utilization. So a quad-channel architecture could pretty much cover the 50% use case. Honestly, a quad-channel architecture is perhaps the easiest solution at this point. Modern server CPUs now support up to 8-channel memory access, which could dramatically improve things with over 1600 bits per second, meeting the bandwidth required for 100% NIC utilization. In fact, AMD claims in their marketing literature for the EPYC 2 Rome server class chips that they can provide 204 gigabytes per second or 1638 gigabits per second, which is the theoretical limit. The technology evangelists will be testing this shortly on a new AMD 7302 server with up to 8 memory channels that he's just recently spun up. So changing the memory architecture is one approach. Another is using a different memory type, something as simple as moving from DDR4 to GDDR6. Here we can see the specification sheet differences between the two products. GDDR6 requires a higher speed clock, but it delivers a 5x performance boost over DDR4. So just moving from single-channel DDR4 to single-channel GDDR6 would easily cover the 50% network utilization use case. Going to dual-channel GDDR6 could support up to 2048 gigabits per second, exceeding the 100% utilization use case. It could even provide some design headroom. So as the von Neumann SmartNIC vendors move forward with new chip designs, things like in-package high bandwidth memory, HBM, and high bandwidth memory 2, or HBM2, become options. We can discuss these in a future video. Finally, as chips go beyond 7 nanometer and designs move to chiplets, other options become available. Thank you for your time.